Unit 6, Day 3, Exponential Growth and Decay. Today we are going to write and evaluate exponential expressions to model growth and decay situations. A function of the form f of x equals a times b to the x power when a is greater than 0 and b is greater than 1 is an exponential growth function, which increases as x increases. When b is between 0 and 1, the function is called an exponential decay function, which decreases as x increases. The graph of the parent function f of x equals 2 to the x power is shown at the right. When we look for the domain of our function, we are looking for our x values. So where does our graph go on our x-axis? It goes from negative infinity to positive infinity, which we also can say as all real numbers. When we look at our range, we want to look at our y values. What is our littlest y value? What is our largest y value? We can see that our graph approaches x, the x-axis, and it goes up to positive infinity. So our range is from 0 to infinity. We can also say that y is greater than 0. Notice as the x values decrease, the graph of the function gets closer to 0. The function never reaches the x-axis because the value of 2x cannot equal 0. In this case, the x-axis is what we call an asymptote. An asymptote is a line that a graph function approaches but never touches. Tell whether the function shows growth or decay, then graph. When we're looking at our function to see if it shows growth or decay, we want to look at our multiplier. In this case, our multiplier is 3/4. So 3/4 means our b is between 0 and 1. So we say that this graph is decay. This 10 right here represents our y-intercept. So when we graph this function, we want to plot a point on 10. It's decay, so it's going to be decreasing, approaching our x-axis, but not crossing it. When we look at example number 2, our multiplier in this case is 1.05. We say that this represents exponential growth because our b is greater than 1. Our 100 in the front here is our y-intercept. So when we graph this function, we need a point on our y-axis at 100. Our graph is coming from our x-axis and increasing to infinity. Example number 3, a bacteria containing 25 milligrams doubles each day. So to write our exponential function, we want to make sure we know how much we start with. 25 is our y-intercept, and we want to know our multiplier is doubling, which means the number 2. So when we write our exponential function, we have f of x is equal to our y-intercept, which is 25. Our multiplier is 2 raised to the x power. So to predict the number of bacteria in 30 days, we can replace our x with 30. So we have f of x, or f of 30, is equal to 25 times 2 to the 30th power. And when we type this into our calculators, we get approximately 2.68 times 10 to the 10th power of bacteria. So we have an extremely large amount of bacteria. Approximately how many days would it take the bacteria to be over 1,000 milligrams? Well, we know 1,000 milligrams represents our y. So if we set 1,000 equal to 25 times 2 to the x power, use inverse operations, we get 40 is equal to the 2 to the x power. To get rid of an x power, we would have to take the xth root of 40 would equal 2. And I am just not sure at this point how to solve this. There has to be another method. You can model growth or decay by a constant percent, increase or decrease with the following formula. The final amount is represented by A of t. Your initial amount is represented by your A. We always use 1 plus or minus depending upon whether it's growth or decay. If it's exponential growth, we're going to use 1 plus. If it's exponential decay, we're going to use 1 minus r. Our r represents our rate of increase. You need to make sure to change your rate from a percent to a decimal. And your t represents your number of time periods. In example 4, in 1981, the Australian humpback whale population was 350. I underline my important information. It increased at a rate of 14% each year. Since then, write a function to model the population growth. So we know we're representing population growth, so we're going to use A of t is equal to A times 1 plus r raised to the t power. So my 350 represents my A because that's my starting amount. My rate is 14%. So we want to make sure and change that to a decimal. So when we plug this information in, we have A of t is equal to 350 times 1 plus 0.14 to the t power. So when we combine our like terms, we have A of t equals 350 times 1.14 to the t power. In 1991, what will the whale population approximately be? Well, notice we started in 1981, so in 1991, our years are 10 years different. So we can evaluate our exponential growth function for 10, which means we're going to replace our t with 10. And when we plug this into our calculators, we get 1,298 whales in 1991. Predict when the population will reach 20,000. So this time we're plugging our 20,000 in for our final amount. 350 times 1.14 to the t power. And again, we're at a situation where we aren't quite sure at this point how to figure out what our years are. But we will eventually be able to solve that. Example number 5, a motor scooter purchased for $1,000 depreciates at an annual rate of 15%. Write an exponential function to model depreciation. So this time it's depreciating, so we want to use 1 minus r. We want to change our rate to a decimal, so we get 0.15. So we have A of t is equal to 1,000 times 1 minus 0.15 to the t power. When we simplify that, we get A of t is equal to 1,000 times 0.85 to the t power. In 5 years, what will the motor scooter be worth? So we evaluate our function for 5. A of 5 is equal to 1,000 times 0.85 to the 5th power. when we plug this into our calculator, after 5 years, we will have, our scooter will be worth $443.71. Predict when the value will fall below 100. We can take a guess. If we were to plug it in, we would put our 100 where our final value goes. And we could make predictions as to how much time it would fall below 100. And if we said anything from 13 to 15 years would be a good prediction. But we are going to learn in future lessons how to find this exact value.